Hello there, I'm Ihan Lelvela and my student number is 2016-030, and this is my presentation on concurrent programming concepts for the concurrent programming module. So without further ado, let's get started. Alright, so in this presentation, I'm going to be covering some of the concurrency concepts, and the concurrency concepts that I'll be covering are race conditions, interference, critical sections, synchronization and synchronization mechanisms, and mutual exclusions. So let us first take a look at race conditions. So what is a race condition? A race condition is an undesirable situation when two processes or threads attempt to perform two or more operations at the same time. So this is a common problem that we find in even in real world. As we know, concurrency issues arise from the real world, and when we try to emulate such situations in computer systems, we face the same issues. So one of the most popular incidents, famous incidents of a race condition issue causing a massive havoc is the Northeast breakout of 2003. So essentially, this was one of the largest breakouts in the power breakouts or blackouts in the history of North America, and this affected both Northeast America and Central Canada. And as you can see in the GIF, uh, this is a this is a GIF of the before and after images of from a satellite taken above these areas. So, what happened? What was the aftermath or the consequences of this issue? Was around 50 million people lost power for up to 2 days in, as I mentioned, the biggest blackout in North American history. And this event also contributed to at least 11 deaths and cost an estimated 6 billion US dollars. So you can see how the how a small issue like a race condition can go a long way. So it is important that we understand what a race condition is and how it can happen and how we can solve it. So going back to the same incident, what has happened is a race condition has occurred in the energy management system. So this energy management system was connected to another alarm event application system, which was looked after by the electrical company. And so what has happened is the race condition in the management system resulted in the alarm event application getting into an infinite loop. And how difficult these kind of problems are, hard, hard, hard to spot is another issue. So although and another aspect of race conditions is the issues that can be caused by race conditions are not um, apparent to someone in the first instance. So that is why the system experts who were in charge of the system were unable to uh, were actually unaware of the malfunction for over 1.1.5 hours. So this fault was so hard to find in the program code that it took weeks of going through these millions of lines of codes and data in order to find it, according to the spokesman of this electrical company, which is First Energy. So there are also other examples of race conditions, such as in computer security, where you can have a attacker gain access to an unsynchronized shared resource through means of race conditions and cause other actors or systems to malfunction. And this could lead to issues like denial of service attacks. And on the other hand, we have file systems where there are two or more programs racing to make changes to a file that can result in data corruption. However, you might have seen most of the new softwares have a lock file that is created whilst they are making changes to a document. So this is to prevent such race condition issues and data corruption. So how do race condition problems occur? They can occur through multiple threads or processes interfering with each other. This is what is known as interference. So let us take a look at the definition of interference. So interference is when two operations running on separate processes or threads modify the same shared resource, that is, overlap in the sequence of steps of the two operations. So let us take a look at a concrete example of interference to understand what this is. So here we have the sequence of steps to the problem. So this problem is actually from a banking account system. So let's assume there's a banking account system and there are two transactions for the same bank account, and we have two separate threads that are processing each of these transactions. So thread A will be processing a deposit or a credit transaction, and thread B will be performing a debit or deposit transaction to the same bank account. So what happens here is, first thread A and thread B both retrieve the current bank account balance. So then the issue here is, um, thread A will, first of all, thread A will compute the bank account balance as rupees 1000 after crediting the amount of the transaction, which is also rupees 1000. By thread B, which does not have the state of, which does not share the same state as thread B, it has a separate state and it computes its bank account balance variable, let's assume, as rupees minus 100 after deducting the amount of the withdrawal transaction amount. So then it becomes rupees minus 100. So let's just assume this is a current bank account with the overdraft facility. So now the problem is, now these two threads are separate, but let's assume that uh, to persist this bank account balance, these two threads have to access or communicate to the main thread, which is having actual access to the persistent memory where the bank account balance is written. Now the problem is, if we do not synchronize these through two uh, threads, two child threads with the main thread, and allow both of these threads simultaneous action to the simultaneous access to the main thread, both of these will write to that bank account balance. So then thread A will write the bank account balance as rupees 1000, thread B will write the bank account balance as rupees minus 100. But now, since both of these have simultaneous access and we do not synchronize these two child threads, what happens is thread A's result is overwritten by thread B. So the issue here is, of course, you can see there is a data inconsistency, data corruption, and another problem is this behavior is unpredictable, because in a different circumstance, it might have been thread B's result that gets lost and overwritten by thread A's value, or there could be no error at all as well. So since this is unpredictable, these bugs can be difficult to detect and to fix. So this is why we need to know how to solve race conditions. So how can we solve race conditions? It is through using proper synchronization mechanisms in critical sections of a concurrent program. So we'll take a look at what are these synchronized mechanisms and what are critical sections. So synchronization and synchronization mechanisms. Uh, Synchronization mechanism is a mechanism that makes sure two or more concurrent processes or threads do not execute a critical section simultaneously. So um, In the case of a banking account example, the concurrent processes or threads might be the thread A and thread B, which were separately executing the two transactions. So what they're telling is these two threads should not be able to execute a critical section simultaneously. So the critical section in the banking account example uh, is the uh, code snippet or the section which allows us to write to the bank account balance. So by allowing these two threads to that same code snippet at the same time simultaneously um, is how race conditions and interference occurs. So to prevent that only we are using synchronization and synchronization mechanisms. So again, going back to the definition of a critical section, it is the code segment that should not be accessed by several threads at the same time. So as I explained, in that case, in the case of the banking account, this code segment would be the code segment in the main thread that allows us to write the bank account balance to persistent memory. This should not be able to access by several threads, that is thread A and thread B in that example, at the same time. Instead, what should happen is the child threads should be given access one at a time, and then their states should get synchronized. So that's why this critical section should be protected using a synchronization mechanism. So one of these synchronization mechanisms is what we call a mutex. So mutex is actually stands for mutually exclusion. So it is a synchronization mechanism which grants a thread or process exclusive access to a shared resource through what is called a lock, and this helps prevent race conditions. So there are some other types of synchronization mechanisms as well, such as condition variables, which are used by competing threads to wait on a given lock to be released. So as I mentioned earlier, only one thread will be allowed to access, one child thread will be allowed to access the main threads or whatever the critical section at a given time. So for the other thread to know when to acquire the lock after it is released, we will be using this condition variable to signal. Um, and then we have semaphores, which is also another mechanism where we hand out a limited number of permits to threads. So a common example of these are database connection pools, where there are a limited number of connections given out at a time, say 10 or 50, and if there are say 100 threads, only the first 50 will be able to get access to the database. The remaining 50 will have to wait on those previous 50 permits to be given to be released. So these semaphores can also be used as a mutex, that is called a binary semaphore, by only giving out one permit. So a key distinction between mutex and semaphores is, in mutex, the same thread which acquires the lock must release the lock, but in semaphores, different threads can acquire the lock while another thread releases the lock. So this is essentially what we wanted to cover today in the what I wanted to cover today in this presentation, that is race conditions, interference, and synchronization mechanisms. So to sum up, there are uh, there are several concurrency related issues that can occur, and it is important for us to understand how these issues may occur so that we can plan for them, and then we should also know what are the different kind of solutions that we can use in order to solve these concurrency issues. So concurrency issues can in modern day computer systems be very critical, and that is why we need to give a significance to that aspect of modern computing systems. So with that, I conclude today's presentation, and thanks for listening.